Hello everybody and welcome back. Today we're going to be talking about Malthusian growth. And so as a little introduction, this comes from the idea of Thomas Malthus, a late 18th and 19th century economist whose central idea was that population growth will always outrun the food supply, and that without strict limits on reproduction, the human population will suffer as a result. And so what that sort of looks like graphically is that if we sort of graph it here, we have the population, which he believed would grow exponentially, just purely exponentially. And so the way that you sort of represent that is by saying, sure, you could say it as e to something, but you could also say that the rate of change of the population with respect to time equals some constant times the population itself. So anyway, so if you have the population growing exponentially, eventually what's going to happen is that this curve that represents the resources, right at this point right here, is where the human population will start to suffer because the population has outgrown the sort of resource capacity of the society. And this was his basic theory, is that eventually we're going to outrun our ability to collect resources and the human population will suffer. But what we can do is look at this mathematically to try to understand it better. So we have, again, just rewriting this, we have the derivative of the population with respect to time equals some constant times the population itself. And so this is, again, a separation of variables. If you don't know how to do the separation of variables, I have a video that talks about it, and you can find that on my YouTube channel. And so essentially what we can do, this process, is we're separating, so we can divide by p on both sides. So 1 over the population times the derivative of the population, and then move this dt term over to the other side, so equals k dt. And then we can integrate indefinitely both sides. And so what we end up with is natural log of the population plus c equals this constant times time plus another c. And again, we can just move this over to the other side and combine like terms with the c because it's just a constant. It can be anything we want. So we can say natural log of the population equals kt plus c. And so the way that then we move on from this is by exponentiating both sides. So we can raise both sides. E to this side equals e to all of this. And so what we end up with is e to the natural log of something is just this. So we have the population. And then on this side, it's a little interesting because we have two terms in the exponent of this e. And a certain exponent rule that we can use is that e to, well, here we can go up here. E to the a plus b equals e to the a times e to the b. So coming down here, we can say that e to the kt times e to the c. But e to the c, e is just a constant, c is just a constant. So really, this entire term is just another constant. So we can say this equals c, another constant, times e to the kt. And so this is how we solve this differential equation. And so this tells us how the population changes over time. And as we can see, just like the graph that we saw on the last screen, we have the population growing at an exponential rate. And so now we're going to look at it graphically and see how this lines up with the resource line. So looking at this growth model for Malthusian growth, what we can see here is that we have, so y equals some constant that we have a slider here, so we can kind of move it around. As you can see, if it's negative, the population is obviously very much so decreasing, but if it's positive, it has this exponential growth. And if we look at it past, let's say time equals 0, and so we have this k value that can kind of determine how quickly it's going. But as we can see, it always intersects with this resource line. So this equation doesn't really come from anywhere. It's just supposed to show a little bit of variation and change, but overall it's pretty consistent in going upward. Resources are increasing over time. And so what this is showing is that eventually the population will outgrow the resource or the amount of resources that we have. So it's at this point right here. And of course, this depends on many different factors. If k is a lot bigger, it'll happen a lot sooner. But if we can kind of reduce k and make it there, it's of course much further away. And in some cases, if we make k 0, or if we make k negative, well, then it's not really going to ever outgrow our resources. And of course, we can try to increase our resources, but in general, this is Thomas Malthus's beliefs.